it to the page titled Ethers. All right, so let's start by going through ethers. So ethers are a homologous series with the general formula CnH2n plus 1, and then there should be an O there at the end. So if you can just add that wee O in. So ethers are a homologous series with the general formula CnH2n plus 1O. They are structural isomers of alcohols, but the properties that they have to alcohols are quite different. So for example, the boiling points of ethers are much lower than alcohols with the same molecular mass. And this is due to the fact that ethers have weak London dispersion forces between molecules, unlike alcohols that have stronger hydrogen bonding between their molecules. Ethers are non-polar molecules and are often used as non-polar solvents, and they are also volatile and highly flammable. Okay. Ethers, I would say, are one of your most common non-polar solvents that will come up as part of Advanced Higher for a couple of reasons. They're a lot easier to work with than solvents, other non-polar solvents like hexane and cyclopentane and things like that, because usually those chemicals are really pretty dangerous and can be carcinogenic, whereas ethers generally are a wee bit safer to work with in a lab setting. So we'll start by looking at naming ethers, and then we'll kind of look at how this links into the structures of our ethers. So ethers have the general structure R bond O bond R dash, where R and R dash are alkyl groups that can be the same or different. Now, ethers can be considered as an alkoxy-alkane. So that kind of gives us a clue about what the name will be. And examples of alkoxy groups are shown below. So we've got CH3O is methoxy, C2H5O is ethoxy, and so on. Do not confuse this with alkoxides, okay? Alkoxides, so not to be confused with alkoxides. So an alkoxide would be a CH3O with a negative charge on it. And then C2H5O with a negative charge on it is ethoxide. Okay. Now we make ethers by reacting with alkoxides, okay? But just try not to confuse the groups. And this little guy here, that's not a negative charge, that's a bond, okay? Think about it as the difference between hydroxide, which is OH with a negative charge on it, and hydroxyl, which is an OH branch. It's the same situation that we get with alkoxy groups and alkoxides, okay? So it's only ever going to be an alkoxy group when it's actually attached to a carbon, whereas it will be an alkoxide if it's a nucleophile on its own reacting, okay? So when naming ethers, the longest chain of carbon atoms provides the alkane part of the ether's name. Now, the example that I've put in here is actually not a good example for our first one that we're going to look at. So we're actually going to draw in a simpler one, and then we'll look at how to do this slightly more complicated one in a moment. So what I'm going to do is just draw out a diagram of an ether that you guys can just copy into this space. like so. Right, so what we've got here is an ether. Ethers are always quite distinctive because they've got two carbon groups on either side of an oxygen. Now, when we are naming this ether, the longest chain of carbon atoms provides the alkane part of the ether's name. So that kind of general name that we used was, I'll actually do this at the other side. So the kind of general name we used to describe all ethers was alkoxy alkanes. So the longest chain of carbon atoms will provide the alkane part of the name. So the longest chain of carbon atoms that we will be able to get in the ether that I've drawn would be 1, 2, 3, because the other side only has 2 carbon atoms in a row, so the longest chain there is 3. So the name for this ether is going to be alkoxypropane, and then we'll go and we'll be specific about the alkoxy. So I could say that's going to be alkoxypropane. And then let's go and name the alkoxy bit. Now, essentially, this is acting like a large branch coming off of the longest chain. It's probably one of the most effective ways to think about this. That's a branch coming off of the longest chain. It doesn't look like a branch, it looks much too large to be a branch. But if we think about it as being like a branch, it does make this a little bit easier. So if we are trying to determine the name of this branch, we're just looking at how many carbon atoms there are. So there's 2 carbon atoms, so that's going to be eth, and then the oxygen atom makes it ethoxy. So this would actually be called ethoxypropane for the name there. Okay. Right, so we'll go on to look at some more examples of these. And we'll look at what happens when the alkoxy branch maybe doesn't come off of the first carbon. Now, we don't need to call these 1-ethoxypropane, because when we are naming ethers, we always assume that the branch is on the first carbon unless stated otherwise. Okay, so it's a little bit different from naming just a regular branch, in the fact that we don't need to use the number 1 if it's on the first carbon. Okay, so what I've got here is a little page with some different formulas, names, and then spaces for diagrams or formulas. So what I'm going to give you guys is just a couple of minutes, maybe like 3 or 4 minutes, to have a go at the first 3 rows in the table. Okay, and then I'm going to show you the 4th row in the table and then get you guys to have a wee go at the last row in the table, and then of course I'm going to put up the answers. So I'm going to give you maybe 4 minutes to have a wee go at filling in as much of this table as you can. If you're really not sure, don't worry about it, just leave it out or draw it in pencil, and then you can make any changes if necessary. So it's 14:32 just now. So I'll come back at 14:36 and start drawing in your answers. So that will give you a time to aim for. So 14:36, we'll be back looking at these answers. Right, so let's have a wee look at the answers for the blanks in the table. So for the first one, we've got the most basic, all ethers, which is methoxymethane. So all we're going to do for this one is our CH3s on each side of our oxygen, like so. And that's our methoxymethane. The next one we've got is ethoxyethane. So looking at the formula, we can see we've got our oxygen in the middle there, and then on each side, we've got C2H5s. So that's exactly what's going to be drawn. Like so. So that gives us the ethoxyethane there. For our next one, we're just given the name of ethoxypropane, and we're not given the kind of shortened structural formula. So in this instance, probably best to look at our name. So we've got propane as the longest number of carbons in the chain. So that tells us 3 carbon atoms in the chain. You can draw these whichever way around you like. So you can have your longest chain on the left and then your alkoxy part on the right, or you can have vice versa. It really doesn't matter. So I'm just going to draw this one so that it kind of matches the name, but they don't always, the structures don't always match the name in terms of you're not always going to have your alkoxy and then your longest chain. So I'm starting with my propane chain. So I'm drawing 3 carbons in my longest chain, popping all the hydrogens on apart from 1 on the end carbon, because I'm going to have my ethoxy branch coming off of that. So I'm going to have my oxygen atom there, and then there's an eth attached to that. So that's going to be 2 carbons. Like so. And then for the formula, it's kind of just counting the carbons and hydrogens on either side of the oxygen. So on the left side of the oxygen, I've got 2 carbons and 5 hydrogens, so C2H5, then an oxygen. And then we've got C3H7 on the right-hand side of the oxygen. So your formula there, C2H5O, C3H7, and that's your ethoxypropane. Right, I'm going to show you how to tackle the fourth one, which we can see is a little bit different because the alkane that forms the longest chain has a branch coming off of it. So we've got ethoxy to methylbutane. So for this one here, I'm going to start by drawing 2-methylbutane. I'm actually just going to draw out 2-methylbutane in its entirety, and then I'll erase one of the hydrogens for our branch, for our alkoxy branch. Right, so that's our 2-methylbutane. And what we have is an ethoxy branch coming off of the 2-methylbutane. Now, the fact that it just says ethoxy and there's not a number before that branch tells us that it must be coming off of the first carbon. Now, because I have chosen to draw my branch here, that must be the second carbon, which makes the carbon on the left carbon number 1, and that's where I must draw my ethoxy branch coming off of. So I'm going to have my oxygen, and then my 2 carbons and my hydrogens. Like so. And then when we go to look at the kind of shortened structural formula for it, it's kind of all the same, except when we get to this part here. So we've got our C2H5, which is that bit there. We've then got our oxygen. We've then got our CH2. Then it's this kind of part in yellow. So we've got our CH and then a CH3 coming off of it. So in order to represent that branch, we use a bracket. So we've got CH representing the carbon and the hydrogen, and then we've got that bracket around the CH3 that tells us that we've got that CH3 branch coming off of the chain. And then finally, we've just got the C2H5 at the end of that name there. So that's how you would kind of tackle things when there's a branch. So again, I'll give you guys a couple of minutes to have a wee go at drawing out the structure and doing the shortened structural formula for prop-oxy 3-methylhexane. I recommend that you draw really small because this is going to be quite a long ether. So I would definitely recommend drawing small in order to be able to fit that in the box. And again, I'll give you guys a couple of minutes. So let's aim for 1444, and then I'll come back and show you the answers for those two, and then we'll continue on with the ethers. Right, so let's have a wee look at our answer here. So we'll begin with the structure. So I'm going to start with 3-methylhexane. So I've got my 6 carbons for my hexane chain. I am going to make the carbon on the left carbon number 1. So just counting along 3 and popping my methyl branch on that 3rd carbon there. Can then pop my hydrogens onto the 3-methylhexane. Like so. And then we've got prop-oxy. Now again, the absence of a number before the alkoxy name tells us that the alkoxy branch, the prop-oxy branch in this case, must come from the 1st carbon, from carbon number 1. Try not to get confused with the 3 that comes after the prop-oxy. That's just telling you where the branch is on the hexane chain. Okay, so the number would need to come before the alkoxy part, and we will have a look at a few examples of those on the next page. So I'm going to erase one of my hydrogens there to make space for that prop-oxy. So this time I've got 3 carbons from that oxygen there. And in terms of my shortened structural formula, it's going to be C3H7, then into the oxygen. Then I'll have C2H5 for those carbons that I've just highlighted there. Then I am into the kind of tricky carbon, which is the carbon with the branch. So we're going to do CH, then bracket CH3, and then the rest of it is just kind of a wee bit more straightforward. That's just 3 carbons, 7 hydrogens. So we will just write that as C3H7 at the end. So definitely a bit trickier for that one there. All right, so I'll give you just a wee moment to make sure that you can, check your diagram versus the one that I've just drawn. You don't need to put any highlights in yours. I've just kind of done that so you know which parts that I'm talking about. And then we'll look at what happens if the alkoxy is coming off of a carbon that's not the first carbon. Okay, so it says special consideration has to be made when naming esters in which the alkoxy part of the ether is branching off of a carbon atom that is in the middle of the alkane part of the molecule. So for example, for this one here, we always need to start with our ethers by finding the longest continuous chain of carbon atoms. And the longest continuous chain of carbon atoms is actually kind of right down the middle there. We've got 3 carbon atoms in the chain. So I'm actually going to go ahead and number those 3 carbon atoms. And then when we are building up the name of our ether, I'm going to pop that in, so that's propane. Now it's not just propane, because as you can see, we have a CH3 branching off of the second carbon. So we would call that 2-methyl propane. Then what we can see is we have another branch, and this time it's our alkoxy branch. So that branch there is methoxy. It's CH3, which is just 1 carbon, so it's the prefix meth, and then the oxygen atom. So that's methoxy. So that would be methoxy 2-methyl propane, but then being specific about where the methoxy branch is branching off of. It's branching off of the second carbon. So that's 2-methoxy 2-methyl propane. So definitely quite a long name there, lots of parts to consider. Okay. So the most important thing, if you've got the structure and you're trying to name the ether from the structure, is to always identify that longest continuous chain of carbons. Okay. So again, we have 3 names given with 3 structural formulas, and then also looking at 3 actual formulas as well. So for this one here, I think some of these boxes are possibly going to be a little bit on the small side, just for drawing these kind of the way that we would want. These will probably look quite strange when they're drawn. Yeah, what I'll do is I'll look at the middle one with you, so that I'm not just doing the most straightforward one, which is the first one, and I'm not doing the most complicated one, which is the last one. So I'm just going to kind of go through how you can get the structure of your ether from its name, and then how we look at doing the formula, because the formula can be a little bit tricky. So we've got 2-methoxy 2-methylbutane. So for this one here, generally when we are drawing the structures of ethers, we want it to look like that. So we want the oxygen right in the middle and then the carbons on each side. So that's kind of what we are going to aim for. Okay, so let's see how we can get our 2-methoxy 2-methylbutane to look like that. So let's see. So what we are going to do is we are going to draw, now it's 2-methoxy. So what I want to do is draw butane like the way I've just drawn it here. So I'm going to number it to make it a wee bit more obvious as to what's going on. So there's 1, 2, 3, and 4. So there's my 4 carbons in my longest chain. So that's my butane chain. But what you can see is I've done it in such a way that the oxygen is coming off of the second carbon. Okay, so the ether part's going to come off of that second carbon. Now it's 2-methyl butane. So I'm also going to have to draw a methyl group on the second carbon. So I'm coming back to my second carbon and I'm drawing a methyl group branching off it there, like so. I'm now just going to pop the hydrogens onto that. So that's me drawing 2-methyl butane, and I've also got the oxygen in coming off of the second carbon, and I know that's the case because it's 2-methoxy. Okay, 2-methoxy, that's what tells me that the oxygen has to come off the second carbon, not the fact that it's 2-methyl. Okay, 2-methyl tells you that there's a methyl group on the second carbon. 2-methoxy tells you that the alkoxy comes off of the second carbon. And then the last part, thankfully, is a wee bit easier. It's just drawing the meth part of methoxy, which is 1 carbon and 3 hydrogens, like so. Now, the next part is to do the formula, and the formula is made a lot easier because of the time spent drawing the structure the way that we've drawn it. So I'm going to start, and again, I'm just going to highlight so you know what I'm talking about. I'm going to start with that methoxy branch. So that's going to be CH3O. And then the next bit is the trickiest part, which is this carbon that's got essentially 2 branches coming off of it. I know strictly speaking it's not 2 branches coming off of it because it's part of the butane chain, but because of the way that we're drawing this and because it's being around an ether, we are going to treat carbon number 1 as if it's a branch when we're writing out this formula. So what we've got is we've got carbon number 2, and then we've got 2 CH3s coming off of it in branches. So I'm opening that bracket, popping a CH3 inside, and then a little 2 on the outside to indicate that I've got 2 of those branches. And then finally, I've got just 2 carbons and 5 hydrogens, which I can just write as C2H5, like so. Okay, so again, I'm going to give you guys a wee bit of time to have a wee go at the first one and the last one, and then I'm going to go over the answers, and then we will do the last part of ethers, and then we will kind of go through carboxylic acids as well. Okay, so I'll give you guys just over 5 minutes, or just about 5 minutes to have a wee go at filling in those other 2 blanks. Do as much as you can. If you're not sure, just get as far as you can and then stop, and I will unmute at 14:59 to go over the answers for the rest of that table. Okay, so I'm going to go over the answers for the rest of this table. So for 2-prop-oxy-propane, it's 2-prop-oxy, which means the alkoxy group is coming off of the second carbon in the propane chain. So what I'm going to do is I'm going to draw propane so that it looks a bit like this. I'm just going to move that up a little bit, give myself a wee bit more space. So that's going to be my propane chain there. And again, just so that we can see it nice and clearly, I'm going to number the 3 carbons in that longest chain, the propane chain. I'll pop the hydrogens on that. Like so. And then it's propoxy, that's 3 carbons with the oxygen. So when we're looking at our shortened structural formula or our formula, it's going to be C3H7O for this first section here. Then the slightly more tricky part, we're going to have CH, and then we're opening a bracket for that CH3 branch. And then we've got another CH3. Now we could actually write CH3 bracket and then put CH3 after it, but what we would more commonly do is actually just write CH3 because ultimately we've kind of got 2 CH3s that are attached to that carbon there and there. That's why we've got the CH3 with a little 2. Generally with shortened structural formula, we are looking at the kind of shortest way to write the formula, so that would be the shortest way to write that formula. Something we see quite a lot at advanced higher, things that are at the end of chains being put inside brackets just because it's the shortest way. And then our final one, we've got 3-ethoxy-2-methylpropane. So this can be one that's really quite tricky to draw, and it's really going to be tough with the space that we've got. So I'm going to start by drawing my pentane chain in such a way that I can easily have the oxygen coming off of that 3rd carbon. I'm going to number the 5 carbons in that pentane chain so we can clearly see that that is the longest chain of carbons. And then it's 2-methylpentane, so I'm going to come to the 2nd carbon on that and pop a methyl branch on it like so. I'm then just going to pop all the hydrogens in, like so. And then it's 3-eth-oxy. So we've already got the 3 and the oxy part dealt with because we've got the oxygen attached to the 3rd carbon, and then it's just eth. So that's just going to be 2 carbons like so. Like that. And then for our shortened structural formula, it's going to be C2H5O for that first part here. Now our next carbon is going to be CH. And then in a bracket, we're having this larger branch of a C2H5. So the part that's got carbon number 4 and 5 on it, we're going to put that as a C2H5. We've then got a CH and a CH3 branching off of it. So we're going to write CH bracket CH3. And then finally, there's another CH3. So what we would probably do is pop a 2 on that bracket there. So rather than having bracket CH3, CH3, we just put a CH3 2 again, just to indicate that there's that there. So I'll leave that up just for a moment to make sure that you've had time to copy kind of anything out that you need to. And then we're going to move on to how we prepare ethers, which is just pure revision from nucleophilic substitution. Okay, so preparation of ethers. So it says ethers are prepared by nucleophilic substitution of monohaloalkanes with alkoxides dissolved in alcohol. So for example 1, we've got the preparation of methoxymethane. Now we do need to be able to choose appropriate chemicals. So if it is methoxy, that means the alkoxide is going to be methoxide. And if it is methane, then that means that we want to make sure that the haloalkane we use is a methane. So like fluoroethane or chloroethane, so on and so forth. So I'm going to take fluoromethane, and we are going to react that with our alkoxide. So it's going to be methoxide. Now, we don't get an alkoxide just on its own. It's usually part of a salt. So I'm going to choose something like sodium methoxide. And that should be dissolved in alcohol. I tend to dissolve it in the alcohol that you would use to make it. So in order to make the alkoxide, in fact, what I'm actually going to do, sorry, don't hate me, is I'm going to pop this into 2 parts. So we're actually going to do step 1, prepare the alkoxide. So to prepare the alkoxide, we are going to take a reactive metal, like for example, sodium, and react it with the alcohol that will create the desired alkoxide. So if we want to make methoxide, then we would use methanol. If we want to make ethoxide, then we would use ethanol. So sodium and methanol will make sodium methoxide. So that's Na plus CH3OH will give us Na plus OCH3. And then we also get hydrogen. So that's step 1, we've prepared the alkoxide, because it's the alkoxide that's our nucleophile. And then step 2 is to do the nucleophilic substitution. So I'm going to take fluoromethane this time, and I'm going to react it with that sodium methoxide that I generated. And I'm going to dissolve that in methanol. And what that will do is it will substitute the halogen for the nucleophile. So we're substituting the fluorine for the methoxide. And that is going to give you methoxymethane. I will give you guys a moment or so to make sure that you have time to copy that in, and then we'll do our second example, and then we will just fly through carboxylic acids because it's pretty much all revision. All right, so our second one is going to be preparation of ethoxypropane. So the first thing that I'm going to want to do is to prepare the alkoxide that we're going to use to react. So again, we will start with step 1, which is to prepare the alkoxide. Now in this case, we are going to use the eth oxide so that we can make ethoxy. So for ethoxide, we will use an alkali metal. I used sodium in the previous example, so I'll use potassium in this one. And since we want to make ethoxide, we're going to react with ethanol. And that will produce potassium ethoxide. And also hydrogen. So that will be potassium plus ethanol. So the alkali metal will take the place of the hydrogen on the hydroxyl group, creating an ionic substance, creating your alkoxide and then your potassium ion in this case. And then for step 2, we're going to do our nucleophilic substitution. Now, since it's just ethoxypropane, what we're going to do is we're going to use a haloalkane in which the halogen is on the first carbon. So for this one here, we are going to use an alkane with 3 carbons in the chain, and then we're going to have our halogen on carbon number 1. So for this one, I'm going to use bromine. Okay. If the alkane was 2-ethoxypropane, then we would need to make sure that the halogen was bonded to the second carbon, because that's where the substitution is going to take place. Okay, so that's how different haloalkanes can give you different ethers. You can get branched ethers in that respect. So because we're just ethoxypropane, we're wanting the substitution to take place on the first carbon, so we want our halogen to be on the first carbon. If we need the substitution to take place on the second carbon, we would have our halogen on the second carbon, and so on. So we are then going to react that with the nucleophile that we generated. So we're going to react with the potassium ethoxide. And that should be dissolved in an alcohol. And for this one, we'll use ethanol because we used ethanol to make it. So all that's going to happen is we will substitute the alkoxide in place of the halogen. So popping in the ethoxide instead of popping the bromine there. And that will give us ethoxypropane, like so. Now, in terms of ethers, there are no reactions that ethers undergo that we need to know about. We use them as solvents and we prepare them with nucleophilic substitution reactions. So that, and of course naming them, that's what you need to know about ethers. Again, I'll just give you a wee moment, making sure you've had time to get that copied in before we go on to look at carboxylic acids. And as far as I remember, absolutely everything that we do on carboxylic acids is revision. So it's just a case of getting the notes in. Okay,